Baker. I currently work for 6 Feet Up in Indianapolis, and this talk is going to be an introduction to the Zope Object Database, or ZODB. You can find me on Twitter as Palin Day, and my email address is also up there. So, a quick description of what the ZODB, or Zope Object Database, is. It's a persistence mechanism that will save Python objects that are in memory to the hard disk. It's ACID compliant, so it's safe for storing your data, and it is standalone and independent of other Zope components, so you don't have to bring in all of Zope to use it. Yes, it is Zope in 2012, so whatever. Covering the ACID compliance. So you might have heard the term ACID compliance come up with SQL databases, probably with NoSQL databases in that they don't have it. Basically, there's 4 properties that that a database needs to have to be ACID compliant. It needs to have atomic operations. So in a canonical example, a bank account, if you're transferring funds from one account to another, you want to perform the deduction from one account and the addition to another account as one single step. You don't want the database to fail in the middle of that and say deduct money from one account while not depositing it, because then you've lost money. So either all of your changes happen or none of them happen to keep your data consistent, which is also the next property. Reads should not see any of that transaction data. So if you do a balance transfer, you should only see valid data in your queries. Also, any transactions that you do should be independent of each other. So if you've got 2 people working on the same data at the same time, and they both commit the change, one of them will happen first, and the other one is going to have to requery the data and update. And finally, there's durability. So that your data is persisted, and it doesn't appear during system failures, except for disk failures, unless you've got some other backup solution. So if you lose power, everything should be safely written to your hard drive or SSD. And most of the NoSQL databases that you hear about won't have this, and they even consider having like eventual consistency, where some queries may get wrong data, but it'll eventually all work out. They consider that to be a good thing, which may or may not be depending on your application. I'm sorry, my computer went to sleep. Okay. So why might you use it? Well, in the way that data is stored in the Zope Object Database is as a hierarchy of objects. So if you've got data where everything is contained as a hierarchy or as a tree, then that's a good fit for the ZODB. Also, if you don't know the structure of your information right off the bat, so you don't have a schema that you need to adhere to, this might be good in a CMS where users might be generating their own content, creating folders and putting files in those, things like that. Also, you need to be aware that the ZODB was written for web applications. So it's operating on the assumption that there are going to be many more reads to the data than there are writes. And to get outside of the web a little bit, the file storage backend, which I'll talk about a little bit more later, could be useful in perhaps games where you would want to just store your objects, or maybe asset workflows for people that are generating animations or something like that. But you might not use it in all cases. So it's not a good fit when you've got data that's really highly relational, where you might have a lot of many-to-many relationships that are just inherent in the data. Also, if your data needs to be accessed by more than one language, like if you need to access it directly from Ruby and Python and Java, this won't be a good fit, because everything that is stored is a Python pickle representation. And currently it is only on Python 2.x. 2.7 does work, but Python 3 is not supported yet. So a little bit about what Python pickles are. They're essentially persisted Python objects. It's taking a Python object out of memory and putting it into a binary or string representation to be sent over the network or written to a file or moved between processes, things like that. It can't store things like network connections or file descriptors, things that are kind of temporal in nature, because it wouldn't really make sense to persist a network connection object. But just about anything else in Python can be saved. So I've got a quick example of just importing pickle from the standard library and also bringing in date time. And we make a dictionary that just contains 2 key value pairs, one for a list of strings and one for a date time object. So we have that dictionary, and then we tell pickle to dump that out into a save.p file. The name is completely arbitrary, so it could be .p. Some people do .pickle. That's really up to you. And then when we want to get the data back in another file, we notice we're just importing pickle, and then we're assigning the values that come out of that save.p file into the data variable. When we print that out, we see that we got the date and the site list back. And you'll also notice I'm printing the class that came back with the date object, and it's datetime, even though we didn't explicitly import that. So those kinds of changes are persisted between accesses to the ZODB. So installing it, if you're using pip, you can use pip install ZODB 3.10.1. You can also use it with easy install or build out, depending on what you're most comfortable with. I will note here that there's pip uses a meta package called ZODB that will pull it all down, but you can't pin that one, and not pinning is bad, so don't do that. Installing the ZODB gives you, there's like 7 dependencies, a few libraries that it needs to use itself. And ZODB itself also provides the transaction, persistent, and BTrees Python libraries. And those are used for interacting with the database and saving data. So here I'm making an example class. This is just a dummy class to kind of show off some of the things, some of the interactions. We have a birthday object that just has a name and a birth date, which in my examples will be a string. And it has a representation method that will just print out the name and the birth date. So we're going to go ahead and create a new database. We've already got it installed. And the way we do that, or the quickest way to get started, is just to use the file storage backend that is included with the ZODB. So we import that. We also import the DB class, which is used as the high-level database API that can handle it, that you can interact with regardless of backend. So we generate our backend object, passing in the name data.fs for the file to store our data in. That name's arbitrary, but data.fs is a convention that's widely used. Then we go ahead and instantiate a database instance using that backend. We grab a connection object with the db.open. And finally, we get our root object. This is the top of the hierarchy I was talking about, by asking the connection to give us the root. So root now points to a persistent object that ZODB created for us and knows how to manage swapping between disk and memory. So now that we've got a handle to our database, we're going to want to save some data. The way that you add data to the database is making a reference to an object from an already persisted object. So here we're associating 2 birthday objects with our root. So that we're taking the Alice key and pointing it to a birthday instance, the Bob key and pointing it to another birthday instance. So in memory, the root has these 2 items and it looks like a dictionary. However, those changes aren't saved yet. We have to explicitly commit them. And we do that with the transaction module. So here I am in the same session, importing transaction and calling transaction.commit. That will write any modified objects to the database. So a little bit more on the transactions. You'll notice that I was just calling transaction.commit. At the top level, transaction has two convenience methods, transaction.commit and transaction.abort. They actually cover up a lot of transaction management details for you. These are probably the two most used things that you'll run across that you're actually calling for the ZODB. So here I'm changing the Alice pointer, or the Alice value, to be a string. So it's no longer pointing to that birthday object, which is kind of just sitting off somewhere by itself in memory. If I call transaction.abort, that change is undone, and I'm pointing back to that object again because we committed that change. It's also worth noting that Plone, I think straight Zope apps and Pyramid have modules that allow you to wrap your HTTP requests with transaction.commit and transaction.abort, so that, say you're processing a form and it fails and you're returning an error code, you can just abort the transaction instead of having to do anything. You can abort the transaction in your middleware during the response rather than having to manage that in your own view function. There's also subtransactions. So these are used where you want to break up a commit into several individual commits. So say you've got a large amount of data that you want to save, but you don't have enough room to pull it all in memory at once because the ZODB tries to keep it, it tries to keep the actual reading of the data out of the file transparent to you, but you can control it a little bit. So say you've got 10,000 objects that you need to update, but you don't want to pull those all into memory at once. You can loop over them and call transaction.commit and pass in true to get subcommits each time. If any of those subcommits fail, then the whole commit fails. Or if any of those subcommits are aborted by calling transaction.commit and passing in false, or I'm sorry, passing in true, then the whole commit will be aborted. But this allows you to kind of break it up and do things in stages and cut down on your memory usage. So you see here, basically I'm just doing two subtransactions, updating the birthdays on the two users that are already created, and then writing the commit at the very end. So querying. So to actually get your data back out, there's nothing special about it, which this was actually kind of threw me for a loop with ZODB when I first started working with it, because it seems like you should have to do something to get it out. But ZODB actually hooks into Python, the language's memory management, and knows, okay, if you haven't touched this object for a while, it's probably okay to move that out to disk, and then when you access it again, pull it back. So that's kind of what's happening under the covers here. We're just accessing the Alice object at root and using the getItem API, and then calling get an attribute .birthday and getting the value off of that. And we can also see that if we just use straight getItem or the dictionary interface for Bob, we just get Bob's instance back. The only real requirement is that you have to get a handle on the root object before you can do anything, and we already saw that when creating a connection. So the actual persistence, like I said, is hooked into the memory management of the Python interpreter, and it's constantly moving files between memory and pickles. These can be saved into a common file, that data.fs I was showing. There's also a way to put a network server in front of a data.fs file, so you can have multiple instances of clients, so multiple instances of a web app, for example. As the most common case, they can all talk to that same file without having to have an actual file handle to it. And there's also a back end for writing your pickles to SQL database tables. The changes are automatically recorded for any object that might inherit from the persistent classes, and those classes are persistent, persistent list, and persistent mapping. So the first object that we created that we were using as root was actually a persistence mapping. And any attributes on those will be handled too. So if I assign a whole tree to my root, but don't make any of those, like the birthday object we have is just inheriting from object, it will still get watched because we're watching the entire tree hanging off of root. But there is an exception. So mutable objects. The ZODB memory management can't really tell easily when a mutable object like a list or a dict changes, because by their very nature they change and have values updated all the time. So there's two ways you can handle that. You can either mark the objects that are pointing to the mutable data structures as changed and then commit the transaction, or you can, instead of using a straight list or a straight dictionary, you can use the persistent list class or the persistent mapping class. So here I'm going to show manually saving a list. I'm sorry for anybody in the back that can't see that bottom one. So with the list, first we're making a list with just a single string in it. That's hello. Then we commit that transaction to make sure it's written. After that, we go ahead and add another string to the list. So here's just goodbye. And we ask the object if it's been marked as changed. And this _p_changed attribute is what ZODB marks and checks to know which items need to be saved out during a commit. So we haven't actually updated it with our change, and it's reporting false. So we force it to be true by assigning true to root._p_changed and commit the transaction, and that will actually write the data. For the dictionary example, I'm using persistent mapping instead of using the curly brace notation for a dictionary. So we say that the root.persistentMap attribute is a persistent mapping instance, and then we put a key value pair of hi/hello in there, and we ask the root object, have you been changed? And it has, because it's aware, and then we go ahead and commit that transaction, so that's written to the database. Something I'll mention, but I won't go into a whole lot of detail here. The ZODB also has undo hooks for some of the backends, and when I say some, I really mean file storage, because I don't believe there are that many backends written for it. Basically, to see if your backend does support undo, you get the backend object, which is here the storage variable, and the database object, which here is the lowercase db. And you can ask either one of those if they support undoing by using the support undo method on both. And that's a required method in the backend API, so that won't be a problem. The way you would use an undo is you can get into the transaction log and pull IDs out, but that was a little bit more complicated than I wanted to get into. And the downside is the more of that undo history you keep, the bigger your data file is going to get. So it can grow pretty big. So it's a good idea to pick some kind of time frame, like we're going to save the last 7 days or last month or whatever of object changes, and then run a cron job with the ZOPack and ZODBpack tools to pack that up and get rid of those changes, or get rid of those expired undos. Okay, so I'm going to switch gears a little bit and talk about the BTrees package that comes with ZODB, and this is actually getting more into the internals of how the ZODB actually stores things on disk and how it performs some of its queries. So normal dictionaries aren't necessarily good for storing a lot of data. So if you've got a lot of key value pairs, that dictionary is actually going to be changing in size many different times as you make it grow. And in order to look up the value associated with a key, it has to run a hash function that generates a unique value, and that has to get updated each time you add. So I forget what the scaling is, but they're in the back end of a dictionary. It will actually create new memory and move stuff over as the dictionary grows. BTrees, or binary trees, are actually a way that you can store the data in a sorted order, and you don't have to rely on hash functions to access your values. And they're a balanced tree of values, so that it's not just a monolithic data structure. It's actually a little bit more complicated. Basically, it's, as implied by binary, it's a tree where you start from the root, you have 2 children, each of those could have 2 children, each of those could have 2 children, and so on. The benefit in terms of using it with ZODB is that accessing a single value doesn't bring the entire structure into memory. So if you were to persist a dictionary that had 10,000 objects and you pull it back out, it's going to pull all 10,000 out. If you put 10,000 objects into a BTree and save that, and you just want one, only that one will come out. So the BTrees package has several modules that are available. This will actually look a little bit like static typing because they optimize for different cases. So inside the BTrees package, there are several modules, and they differentiate each other by the first 2 letters of each module. If there's capital case O, then it stands for any arbitrary object. And if it has a capital I, then it's a 32-bit signed integer. So if you access the btrees.io BTree interface package, that means that the keys on all of the BTree objects coming out of there will have to be 32-bit signed integers, and then the values can be any arbitrary object. There's four variations of that. So OO BTree for having arbitrary objects as keys and values. IO BTree that I mentioned before. OI BTree, that's the reverse, so arbitrary objects as the keys and signed integers as values. And then integer key and value trees. In ZODB 3.4, they also introduced an IF BTree with signed integer keys and 32-bit C floats for values. I haven't really seen that one anywhere though. So, like I said before, they behave largely like dictionaries. So when you work with it in your code, you'll notice, like if you do a dir on it, you'll notice they have a keys, values, and items method, and they support the get item interface, so the angle bracket, or the bracket dictionary lookup. The thing that's tripped me up with it though is all 3 of these methods, the keys, the values, and the items, those are all lazy. So if you say btree.keys, you're not going to get back a list of keys like you would with a normal dictionary. You're going to get an items object. That item object will not give you your values until you fully instantiate, or until you force iteration over the entire list. So if you pass that items object to something like len or list, or use it in a list comprehension, then you'll iterate over everything and you'll actually get each of the items. So it could be the keys, the items, or the items, tuples, and the values. These aren't consumed like Python iterators. They actually predate the iterator interface. So one difference is you can call it multiple times. It's not consumed and then you have to recreate it if you need to do it. But if you do want to use the Python iterator interface, they have iter keys, iter values, and iter items if you want to call that instead, which will then produce stuff using the Python iterator interface. So there are some gotchas that you need to be aware of if you're manually building BTrees. you want to use only really simple and immutable data types as your keys. So there's a reason that they have those IOB trees, so that the integer is the key. They don't take up a whole lot of space, and they're very easy to compare. Because the sorting and the searching relies heavily on comparing each of the keys to each other. It's using invariants that are inherent in the integer data type to go through the list and find exactly what you're looking for. And because of that, if you can't easily compare objects, like if you use multiple data types for your keys, so if some of your keys are strings and some of them are integers, you're probably going to get data corruption, and it's not going to know what to do with it. So only once you're using some data type as keys into the database, into the BTree, just keep using that one. If you're making a custom class that you want to use inside of the BTree for keys, then you must define a CMP method. And you'll want to refer to the documentation for this, because there are a lot of conditions that have to be held true in the CMP interface. Otherwise, it will, again, return bad results and not know how to search correctly. And then finally, you can, but you shouldn't use persistent objects or anything that inherits from a persistent class as keys. The reason for this is actually the implementation details of the ZODB. The way that a persistent object is managed in memory versus a BTree are actually conflicting, and the lookup won't necessarily go in the right place all the time. Something else to be aware of, like dictionaries and lists, if you're iterating over it in a for loop, you shouldn't delete items in the middle of it. It's not as strict as Python is with the standard dictionary and list types, but it will cause problems because your iteration won't know where it's at if you start deleting items out of it. So because the ZODB is a hierarchy of objects, you could just search it recursively, but that could be a little slow. So if you want to add indexing capabilities to the ZODB, you're actually going to need to use some other package. Most of the ones that people use are wrapping zope.index at their core, so you have to bring in a little bit more Zope. Zope.catalog is an option if you're using a straight Zope application, which I don't know that too many people are. Plone also has its own customized catalogs, and if you're looking for something that's just more generic, you don't want to use it in a web interface, or you don't want the weight of Zope and Plone, repoze.catalog is a much better solution, but it does much less for you. There is some manual work you're going to have to do to build that index catalog. So just an overview of the repoze.catalog library. Essentially, it is creating a persistent object of the catalog class, and usually it will store it at the root of the ZODB, so it's easy to get to, but you can stick it wherever you want. And then what you'll have to do is associate your own index functions, which you're basically just assigning the functions to a key, just like a dictionary key, to the catalog. So if you want to have an index on, say, the birthday attribute that we had earlier, we would have to define a birthday index called birthday that pointed to a function that retrieved the birthday attribute, off of any object that gets indexed. So when you're putting the objects in the catalog, you'll need to provide an ID and the object that will need to be looked up. And the IDs have to be unique per catalog, or per index, I'm sorry. And your index functions, like I said, are actually going to be fairly simple. All they should really do is take an object, look in that object to see if it has a specified attribute. So there's two arguments, the object and the attribute. If that attribute is on the object, return it. And if it's not, return a default value. So you return none or whatever you want to put there to count as a null. And then the catalog will store whatever result comes back if it's not none. So that's the setup you have to do. You also have to keep track of the ID to object mapping. So if you call it and give it ID1 and some object or some instance, you have to know which object went in with ID1. And usually that's going to be accomplished just by using the pre-existing attribute on the object, like an ID attribute that you make yourself. There are also some relational add-ons to the ZODB to give it kind of relational support. The biggest one is, or the most used one, is the zc.relation. Sorry, most used outside of Plone. This one requires a lot of manual setup, and it's actually a lot more work than even repoze.catalog. But the documentation is really interesting to read because it's got a lot of database theory in it. As far as I'm aware, it seems unmaintained. The last change I saw was from 2008. But Plone is using it if you use the Dexterity Dexterity framework. And if you're really looking for just basic relational stuff, it may just be easier to build a relational index using repoze.catalog rather than relying on zc.relation, where you just have two IDs in the table. So ZODB was written for the web. I assume that makes it web scale, but not in the Mongo sense. But actually it is for smaller deployments. So you can use the ZO server that I mentioned earlier to kind of sit in front of a data.fs file and serve that out to more than one client application. You can also use the rel storage backend, and that will actually kind of treat your databases as a black box from that point. So if you're using rel storage, you can actually take advantage of the scaling techniques that you might use for a relational database. So you want to store your stuff in Postgres, you can put the Postgres databases behind a PG connection, bouncer, or pooler, or whatever, and use that. The Zope Corporation that created this also offers a commercial Zope replication service so that ZODB instances or ZO servers can replicate between each other, and you can have multiple instances. And the gosep.zo raid package provides some RAID-like properties, so you can use that to get more durability. So you can have a master and a slave for your data files, and you can also, I believe, create two data files to use separately to speed up lookup. So like I mentioned before, rel storage takes any data fed to it and converts it into a format suitable for storing in a SQL database. But it's not an ORM, so it's not doing a literal mapping of stuff to a SQL schema. It has its own internal schema that it uses, and most of the actual data is going to be stored as blobs in the tables. It also includes a few helper utilities. So if you want to move back and forth between rel storage and file storage, so you've got Postgres servers in production, but locally you just want to use the file storage, you can use the ZODB convert tool that comes with it to move the files back and forth if you need to. And it's also, again, useful for scaling out the ZODB because you can just rely on the normal stuff you're using already for any other relational databases to scale. You also have repoze.evolution if you would want to do something like a data migration that, like for South provides data migrations for Django, so repoze.evolution provides something similar. You can define schemas with some other Zope packages, but repoze.evolution helps in the sense that you may define a bunch of classes and find out later, I need to add an attribute, or I need to remove that, or I'm changing a generator, or a function that generates an attribute inside of the class. So I need to go into my database and update that. Repoze.evolution gives you a way to do that. And essentially, it allows you to define a function that takes the root of the database as an argument, and then from there you can do whatever. You can recurse over the database, you can look up stuff in catalogs if you've got them, you can force catalog updates, that kind of stuff. So yeah, that's largely used in pyramid applications at this point, I believe. If you're going to be adventuresome and perhaps put ZODB inside of Django for some reason, or Flask, there are libraries for doing that allow you to set up, like the Django ZODB allows you to, in your Django settings.py file, set up all the information you need to point to a data.fs file. And it also provides wrappers for the persistent classes that are more aware of the web framework you're using. And also, the pyramid documentation has a section on traversal, which basically maps your URLs to ZODB objects. So your URLs are your queries. And that's how a lot of Zope applications were developed in the past. So you can find this talk at this URL if you want to look up any of that information. I've also got links in there to some other documentation the BTrees documentation can give you a little bit more detail on the internals. Rel storage also. And Chris Madonna has a good overview talk of the ZODB from PyCon 2011. So that's all I have. Does anyone have any questions? Yeah.
Can you give just a couple examples of where the Zope Object Database is used, like in production?
Yeah, so the question was, can I provide some examples of where the Zope Object Database is used in production? So my company, 6 Feet Up, we use it in Plone applications. So pretty much any Plone application is also interfacing with the ZODB. I'm not currently aware of pyramid sites that are developed with it. We also, well, we have a few internal pyramid sites that use it. I can't give you any big names though, off the top of my head. Most often you're probably going to see it being used by Plone agencies.
There are some bioinformatics databases which use ZOD because of the hierarchical structure, because there is no need for it to convert those structures into a relational format. You can store them as they're related. So that's one of the non-web pattern management system uses ZOD.
Okay, someone from the audience said that there's also bioinformatics libraries that use it because they don't have to convert between the objects and SQL implementation. So. Anything else? Yeah. Sure.
You said that it's not compatible with Python 3 yet.
Yes.
Moving forward, is that being worked on?
It's a goal, but I don't believe it's actively being worked on. The people who have driven a lot of the internal development are busy with other things. And with a lot of the Zope stuff, not just ZODB, but a lot of those packages, they have lost a lot of contributors recently, which is unfortunate. So they have stated they want it to be on Python 3, but it's not actively being worked on. Okay. Well, thank you very much.